If a chemical species can act as either an acid or a base, we call that amphiprotic or amphoteric. Amphoteric is more generic, but amphiprotic is the protic part means you can add a proton or you can subtract a proton, right? It can act as a base or it can act as an acid. So these species that are listed here are all amphiprotic. HCO3 minus can act as an acid and lose this hydrogen or lose this proton, or you can add a proton, an H plus, to make it H2CO3, right? If you have polyprotic acids or acids that have more than one proton that could be removed, then usually the intermediate species are all amphiprotic. So for example, phosphoric acid, which is H3PO4, could lose one hydrogen or one proton to be H2PO4 minus, or it could lose a second proton to be HPO4 2 minus. And it could lose its third to just be phosphate, PO4 3 minus. But these two intermediate species are both amphiprotic because they could either accept a proton or donate a proton. So the hydrogen sulfite ion HSO3 minus is amphiprotic. This process that I'm about to walk through is pretty common for things that I would ask you to do or that you need to know how to do in order to do equilibrium with acids and bases. So we need to write the chemical equation for the reaction of the hydrogen sulfite ion with water, in which the ion acts as an acid. So we need to pay attention that this ion is going to act as an acid. So on the reactant side, we're going to have HSO3 minus plus water, right? React with water. And then this ion is going to act like an acid. So if you remember our Bronsted-Lowry definition, the acid is going to donate a proton. So on the product side, this is going to be the same molecule except for the lack of a proton. So we would write this way: HSO3 minus plus water on our reactant side goes to the sulfite anion that's lost that hydrogen, that proton, right? So now it's SO3 2 minus. Okay, charges are important here. And that proton has now attached itself to the water. So the water is acting as a base. The hydrogen sulfite anion is acting as an acid. We can also write this, the reaction of hydrogen sulfite ion with water in which the ion acts as a base. So in that case, my hydrogen sulfite is going to accept a proton from water. So the reactants are the same, hydrogen sulfite plus water, but in that case, you're accepting a proton to become sulfurous acid, H2SO3, plus hydroxide, right? So water's donating a proton, so it's acting as the acid, and what you're left over with is the hydroxide. It's important to pay attention to how the question is written, especially if you're talking about an ion or something that is amphiprotic. Is it asking that the ion is acting as an acid, or is it acting that it's acting as a base? We'll be comparing later which one of these is more likely. We'd be comparing either the Ka value or the equilibrium constant for this reaction. We can compare that to the equilibrium constant for this reaction and compare which is stronger, so which one is more likely to happen. We already know that water is amphoteric or amphiprotic. In pure water, a few molecules act as a base and a few molecules act as an acid. So about 2 in a billion water molecules will undergo this reaction that's provided here, where one water molecule is going to act as an acid and donate a proton to a different water molecule that is acting as a base. So we're going to have H3O plus or hydronium in that water plus hydroxide ions. This reaction where the water molecule is reacting with another water molecule, and one of them is acting as an acid, one of them is acting as a base. This is referred to autoionization. And you can do this in not just water, but you could do this in ammonia or lots of other solvents that you can think of. This autoionization reaction is the fundamental basis for our pH scale. Okay, so how that gets tied together. Okay, if we think about the equilibrium constant expression for this reaction, remember that pure liquids do not participate. in that equilibrium constant expression. So we're just going to have our Kc is just going to equal H3O plus times OH minus. And we're going to give that a special name called Kw because it's the equilibrium constant for the autoionization of water, right? So the W means water. This value is a constant value at 25 degrees Celsius at any specific temperature. But at 25 degrees Celsius, standard temperature, it is 1 times 10 to the minus 14. So we can use that value and create an ice table to calculate the concentrations of hydronium and hydroxide in a neutral solution. So let's just presume there's no other acids or bases present. When we set up our ice table, we're going to get an X. Some amount is formed and some amount is formed, and it's both X. Okay, so I get X squared equals my Kw value. If I solve for X, then I get 1 times 10 to the minus 7. Now, if you've dealt with pH before, you know that pH is minus the log of the hydronium ion concentration or the H plus concentration. And if you take minus the log of 1 times 10 to the minus 7, you get 7. So a neutral solution of water, right, has a pH of 7. Just a pure water solution should be a pH of 7 because the only place that there are ions coming from is from this autoionization of water. We can think about how Kw changes as a function of temperature. So if we remember that Kw is the rate constant in the forward direction over the rate constant in the reverse direction, and those rate constants are related to the temperature, right? As we increase the temperature, we're going to increase our rate constants. If we change the temperature, that means we're going to change this Kw, and that's going to change the pH of neutral water. So if we look at this simulation that I found online, we start at 25 degrees Celsius, and I can calculate the pH. So the pH is going to be 7 there. Neutral pH is 7. Your Kw is 1 times 10 to the minus 14. If I increase the temperature, okay, maybe to 30, okay, I can calculate Kw. I can determine Kw is 1.46 times 10 to the minus 14. That puts your neutral pH at 6.92, so it's a little bit lower than you might expect. Okay, so here is my initial point. Now I'm going to be lowering my pH as I increase my temperature. So I'm going to go up to 40, calculate that. There we go. Now my neutral pH is even lower. I can go to 45, calculate that. I can go up to, let's see, let's go to 70 degrees Celsius and calculate that. There it is. Maybe not surprising that this neutral right here, this white space, right, is your neutral, and that is decreasing as you increase the temperature. That means it will also increase if you decrease the temperature. So if I go to 10 degrees Celsius, and calculate that. Now I'm over here, my neutral pH is 7.26. And again, remember, this is because the equilibrium constant, Kw, is also equal to the rate constants, right? The ratio of the rate constants in the forward direction over the rate constant in the reverse direction. So as I change the temperature, I change those rate constants, and the ratio of them is going to change.